Kia ora, koutou, nā mai haere mai. Thank you very much for turning out of this talk of Wellington Branch Hochstetter lecture. It's great to see a full house, so thanks to everyone for making the effort to coming out to see our esteemed speaker tonight. Can I just check online that people can hear us? Is all good? Cool, thank you. Right, I'll just give a brief biography of John Townend, this year's Hochstetter Lecture for the Geoscience Society of New Zealand. John was born and grew up in Rotorua. He went to University of Otago and did a BSc Honours degree in 1995, working on the eruption of Rotomahana. He then spent 2 years working at Institute of Geological and Nuclear Sciences, and followed by a year at the Japan Marine Science and Technology Centre. He completed his PhD in 2003 in geophysics at Stanford University, California. At that point, he came back to New Zealand and took a position at Victoria University of Wellington, Te Heranga Waka, where he's subsequently been appointed professor in 2017. And also served as head of the School of Geography, Environment and Earth Sciences between 2016 and 2019. He's worked on numerous projects and in particular has led the Natural Hazards Commission Toka Ao Ake program in earthquake seismology and tectonic geodesy for more than 20 years. He's been the principal investigator of numerous projects in the Marsden Fund, as well as associate investigator. Has led Catalyst-funded projects as well as Smart Ideas and in recent times as associate investigator in the Ngānaru Wakapuke Endeavour program. He's a former president of the New Zealand Geophysical Society and also a former president of the Seismological Society of America, and now serves as the Society's Publications Committee Chair. In 2022, John was elected a Fellow, Hooray, of the Royal Society Te Aparangi, and in 2024 he was awarded the Geoscience Society of New Zealand's Hochstetter Lectureship. So with pleasure I'd like to invite John up to give this year's Hochstetter Lecture.
Kia ora, Scott. Ko ranginui kei runga, ko papatu anuku kei raro, ko ngā tangata kei wainganui. Tihei mauri ora. Nō reira, tēnā koutou, tēnā tātou katoa. Good evening, everybody. Thank you very much for coming out to hear what is going to be the final Hochstetter Lecture for this year, and actually the final Hochstetter Lecture ever, because this particular series of lectures is ending this year, and next year there'll be something different to replace it. I, this evening, would like to try and tell you about some of the adventures I've been having over the last few years on the Alpine Fault. And in particular, I'm trying to give you some idea about what's new and exciting, but also I'd like to be a little bit provocative towards the end of the talk about what we might be doing in a bit more detail. So, in terms of what I'd like to cover today, we've only got the one slide for this evening. There we are. What I'd like to cover is, first of all, just to give you a little background to this talk and to myself, and also some of the links, tenuous that they may be, to Hochstetter. I'm going to introduce what I think is an absolutely unparalleled record of past Alpine Fault earthquakes called the paleoseismic record, which many people in this audience have contributed to. And then I'm going to speak about some of the projects I've been involved with over the last few years. The Deep Fault Drilling Project, Samba, Salsa, Dwarves, a number of other humorously named seismological studies. And then I'm just very briefly going to talk about sort of an exciting new area in which we are moving beyond just using dozens or even 100 seismometers and starting to use thousands and thousands of seismometers. I'd like to finish and spend quite a bit of time talking about some of the lessons about how we reconcile the measurements we make at the present day with the paleoseismic record, and think about what that means for the future and what we might want to do to prepare for that. And I should emphasize that I'm really I'm not going to be focusing on the hazard posed by Alpine Fault earthquakes today. I'm really focusing on the science of earthquakes. And that's certainly not to diminish the incredible work that's being done on the hazard aspect of the Alpine Fault, some of which I've contributed to, but today really the focus is on the interesting science that underpins our hazard assessments. So you've heard a little bit about my background, but broadly speaking, I was born and grew up in Rotorua. I spent a little bit of time as a child living in Murchison and in Hokitika. I then, after I finished high school, I went to Japan and spent a year studying there before I went to Otago University, as Scott said, and studied geology. My first link to Hokitika is that I did my honours dissertation on the 1886 eruption of Rotomahana near Lake Tarawera, or near Tarawera Maunga. This is a picture from an atlas that Hochstetter and a colleague, Petermann, published in 1864 after Hochstetter had left New Zealand, and it's their map of Lake Rotomahana, which now looks nothing like this. And it looks nothing like this because the whole lake was eviscerated when Tarawera and the neighbouring area blew up. I then spent time working, as Scott said, at GNS Science and at JAMSTEC in Japan, and then spent several years in California doing my PhD. I've been very fortunate over the last 15 years or so to work on a broad range of projects up and down New Zealand, from Northland, in fact, all the way down to the southernmost South Island, and all the bits in between. And I've also been fortunate to work on projects overseas in a number of different places. Most of these have had to do with earthquakes, and most of those earthquakes have happened naturally, but the odd one, including one in Korea, was anthropogenically triggered. And so that's been an area I've become increasingly interested in over the last few years. A constant fascination for me, however, has been the Alpine Fault. And I first met the Alpine Fault 30 years ago, a week or two ago, when I was a third-year student in geology at Otago University. And as happened every year, we did a big field trip from Dunedin through central Otago and up the Alpine Fault. And that was the first time I saw the fault. And since I've returned to New Zealand, I've really enjoyed working on that. And we'll cover some of that ground today. This second image here is another link to Hochstetter. It also comes from the 1864 Atlas. And it's of the Nelson region, where I was just a few weeks ago for an earthquake science conference at Lake Rotuiti, St Arnaud. The Alpine Fault doesn't appear on this, because in the mid-19th century, the Alpine Fault hadn't been recognised. But just very quickly to draw this thread to a close, interestingly, when I finished my study of Rotomahana and did my honours, and I graduated from Otago, my godmother gave me a copy of that atlas, a first edition copy of that atlas, which I stored very carefully, and I've looked after very carefully ever since. And I did think of bringing it on this trip, but it remains at home, safely locked up. So, I thought I'd just introduce the Alpine Fault by making the point that it wasn't really recognised until the 1940s, when Harold Wellman and a colleague were mapping in southwestland, which was real tiger country back then. It was very remote, and they did a lot of really important mapping over the course of just a short period of time, actually. But a publication that came out in 1942 really put their measurements together in a very elegant way and demonstrated that there was a large structure, shown here in a rotated format, just so you're not confused. The South Island's been rotated so that the Alpine Fault now runs horizontally along the page. And in this paper, Wellman and Willett demonstrated the offset that had occurred on the Alpine Fault over several million years, and also documented some of the physiographic features that enabled them to recognise this fault in the field. Hochstetter was, in a sense, Wellman was the first Hochstetter lecturer, although he wasn't actually. He, in 1974, was chosen to deliver a national lecture tour, which he did. And at that time, it wasn't called the Hochstetter series. It was actually named after that. But I'd like to think, for the purposes of this talk and the topic of this talk, that Wellman gave the first Hochstetter lecture. It was 50 years ago, and we're bringing it to a close, at least as it's currently named, this year. So, a little bit of sort of insight into the way I think about earthquakes and how they operate. And this is a very personal view, but we're going to return to some of these threads as we go through the talk. So, in essence, earthquakes involve the frictional sliding of one block of rock past another one. And the way that sliding occurs is governed by the stresses that are imposed on the faults and by the properties of the rocks that are involved. Now, generally, if you drill into the Earth's crust, you find that the rocks are saturated with fluids. And fluids typically are water, sometimes hot water in geothermal systems. It might be oil sometimes, it might be gas. Increasingly, people are looking for hydrogen. But in any case, rocks are almost always saturated with fluids. And the pressures of those fluids act to counter some of the stresses acting on faults and cause faults to slide more easily. So something as innocuous as water in the Earth's crust can play a very important role in the genesis of earthquakes. Now, the pressures are governed by how easily fluid can move through the rock mass. And to put it in simple terms, if we have rocks which which make it very difficult for fluid to flow through them, we call them tight or low permeability. And that enables, if you squeeze those rocks fast enough, you can build up quite substantial fluid pressures which weaken the faults, as I've just mentioned. And alternatively, if you have rocks which enable the ready flow of fluid, those are high permeability rocks, and in that case, you typically don't build up particularly high fluid pressures. Now, permeability is a complicated sort of parameter, but as far as we can tell, it's controlled by things like chemistry and temperature and time and stress. And those factors, chemistry, temperature, stress, are basically controlled by the tectonics of the region. So in the New Zealand context, they're ultimately controlled by the interaction of the Pacific plate with the Australian plate. But on top of that, we have to worry about something that controls the distribution of fluids, and that's hydrology. And the West Coast, it may come as a bit of a surprise, but it does rain on the West Coast quite a lot. And that rain turns out, as far as we can tell, to play an important role in many of the processes associated with Alpine Fault earthquakes. So that's the way I view the system in my mind. And it might not be particularly helpful, but we are going to return to it later. The thing that makes earthquakes a fascinating area of study is that the processes that they involve span a very broad range of timescales. So to a seismologist like me, the timescales that we're most used to thinking about are really fractions of a second up to several seconds or maybe minutes in the case of a very large earthquake rupture. We'll see some at the end of the talk. But then for big faults like the Alpine Fault, that period of really intense activity is followed by years, decades, perhaps centuries, even longer, what we call the interseismic period, in which time the fault is equilibrating, it's preparing for the next earthquake, it's being reloaded in a sense. And so that's a much longer time scale than what happens when an earthquake's actually occurring. And then if you step back and you take the view, as Harold Wellman did, for example, of a fault representing many hundreds of kilometers of offset recorded over many millions of years, then that's a much different timescale again. So when we're thinking about something like the Alpine Fault and we're thinking about how does it generate earthquakes, why does it generate them in particular places, and what governs the timing between one earthquake and the next, we're sort of grappling with this broad range of timescales. I thought I'd just provide a little historical context here, illustrated by these two diagrams. The one on the left is the front page of a paper that was written only 18 or so years ago, in which the title of the paper was, "Do Great Earthquakes, Earthquakes Larger than Magnitude 8, Occur on the Alpine Fault in the Central South Island, New Zealand?" And this was a live, important question, and it was worked on by serious scientists, because at the time there was quite some debate about whether or not the Alpine Fault could generate earthquakes of magnitude 8 or larger. In the intervening time, and building upon earlier studies, there's been a huge amount of work done to understand the chronology and the extent of past earthquakes. And we call this paleoseismology, and there's at least one expert in the room. I'm sure there are many others who I haven't spotted yet. But this is looking at the geological and the geomorphic signatures of earthquakes which have occurred over the past few hundreds of years, thousands of years, perhaps even longer. And this diagram on the right-hand side from one of Jamie Houth's papers, the most recent one I think, summarizes the record of large earthquakes, which are indicated by these colored bars. Each colored bar represents an earthquake And the fault itself is illustrated down the bottom from Lake Carniere, which is up towards Hokitika on the left, and the area south of Haast over on the right-hand side. And so the length of the bar tells you how far an inferred earthquake has ruptured, and the height of that bar tells you when it took place. Now, this is extremely hard-won information because it involves collecting cores in lakes and digging trenches in certain places and looking at the stratigraphy exposed in different parts of the fault and putting that all together. And it's complicated because the record at any one location, like this lake in the middle here, Lake Paringa, the record here consists of a whole bunch of little red histograms telling us something about when an earthquake is inferred to have occurred at Lake Paringa. But in order to relate that to the fault as a whole and to give it some context, give it a magnitude, you have to be able to relate that record to the records from the adjacent lakes and beyond. And so that's why it's a very complicated but absolutely important component of understanding how faults work. And the record of earthquakes from the Alpine Fault is, I think, unparalleled in the world in terms of the length of the record, the clarity with which we see certain signals, and also what it tells us about when we might expect earthquakes in the future. So just to pull out a few figures, and there are lots of figures on this diagram, but I just want to pull out a few key ones. As far as we can tell, the last major earthquake, which was probably of the order of magnitude 8 or even larger, ruptured the three main sections of the fault, the southwestern section in green, the central section, and the northwestern section, in 1717, current era, 1717 AD. That is roughly 308 years ago or something. The recurrence interval, the time between one big earthquake and the next on the Alpine Fault on the central section, is something like 249 years plus or minus 58 years. And that number is incredibly well determined, and it describes an almost regular, not clockwork, but a very regular pattern of large earthquakes. So if you compare that average recurrence interval of 249 years with the 308 years that have elapsed since the last big earthquake, you realize that we are late in the typical cycle. That's not to say we're overdue, but we are late in what is a well-estimated, well-quantified cycle. So if you take those numbers and you crunch them, and this is work again that Jamie has led, you come up with an estimate of a big earthquake rupturing the central section of the Alpine Fault in the next 50 years of about 75%, albeit with uncertainties. There's uncertainties on that number, but that's a very high likelihood. You can do some further simulations, and they suggest that there's something like an 82% probability of that earthquake rupturing the southwestern section as well, the green part down here, and that would be a magnitude 8 plus earthquake. Now, what the paleoseismic record also shows us is that there are certain key parts of the fault, and in particular, the junctions between one segment, well, I'll show it here, between one segment and the next, here, south of Haast, here near Inchbonny. These intersections seem to play a particularly important role in both the nucleation, the origin of earthquakes, and also where they tend to stop. Sometimes these locations act as barriers to an earthquake propagating through. They stop an earthquake and they constrain it to one or two segments. At other times, they let it go ripping through. So they behave a little bit like a gate. Sometimes they're open, sometimes they're closed. So I'm really interested in what sort of factors control this behavior. What are the geometric or structural, the hydrological, the water-related or rheological factors, that is to do with the way rocks deform, that control both the timing of big earthquakes and where they nucleate and where they propagate. So that sort of thread underpins a lot of what I'll be talking about later. The other reason I'm particularly interested in these gates and the segmentation of the fault is because what happens when the next big earthquake occurs, the shaking that we get at any particular location, and here I'm going to pick on Christchurch, but the shaking you get depends on what happens on the fault, the fault pattern of slip, where the earthquake nucleated, where it stopped, etc. And it also depends on how the waves, the seismic waves, propagate out, in this case through the South Island, and shake different parts of the countryside. So here's a simulation that Caroline made, yes, Caroline, and it's a very simple representation of what might happen. It treats the Alpine Fault as just a rectangle, just a perfectly straight rectangle, and she's considered 3 scenarios. And I'd just like to say before I go any further, as a lecturer at this university, I find the multiple screens very difficult to work with. And I'm sure they are for you too. So I'm just going to move over here a little bit. In this scenario A, the earthquake starts at the red star in the northern end, and it ruptures towards the south. Most of the slip takes place in the southern end. That's represented by the yellow colours. And this is the pattern of shaking you would get at a particular location in Christchurch. And you can see the shaking goes on for a long period of time, for tens, perhaps hundreds of seconds. But it's quite low amplitude. The amount of shaking is not very long, but is not very much, but it goes on for a long time. Scenario C down the bottom is basically the scenario A flipped backwards. Now the earthquake starts down here, it ruptures towards the north, most of the slip is at the northern end. And in contrast to scenario A, now you get a much higher amplitude of shaking, much more shaking, but it's compressed in time. It doesn't go on for so long. And the one in the middle, it's like Goldilocks and the 3 Bears. This is just the ideal case. This is when it starts in the south, it ruptures most of the fault, and it produces a lot of slip along several hundred kilometers of fault. And in that case, you get both a long duration of shaking and a high amplitude. So, as I said, these are simple representations of what might happen. I think Caroline would agree with me that these are simplistic, idealized pictures. But they give you the idea that we should be doing all we can to understand what has happened in past earthquakes in terms of where the fault slipped and how far and how much, but also what we might anticipate in the future. So, what I'd like to do now is just do a quick tour of some of the projects I've been involved with over the last few years, starting with this one here called the Deep Fault Drilling Project. This project we started drilling in 2011, and we had a number of quite big, quite ambitious sorts of questions to answer, such as how do large plate boundary faults like the Alpine Fault evolve? What is their internal structure? Are they just an infinitesimally narrow zone, or are they a broad zone of multiple strands of fault with unusual characteristics? How do they behave during an earthquake? What controls the timing of those earthquakes? And basically, what is the state of health of the Alpine Fault late in its typical earthquake cycle? We wanted to measure the temperature, the pressure, the permeability, the stress, all those parameters I mentioned earlier, late in the cycle before the next big earthquake. Now, when big earthquakes occur, seismologists, geophysicists, geologists rush out and often drill holes into the fault to measure all sorts of parameters. And that is incredibly important science. But at the same time, the horse has bolted. The earthquake has happened. And so what you're measuring then is the residual stresses, the post-earthquake temperatures, etc., etc. So we wanted to measure the state of the health before it ruptured so that we could feed that into the global efforts to understand the conditions under which earthquakes nucleate. So we started quite small, actually. We went to a place called Gaunt Creek, which is on the west coast, about halfway between, south of Whataroa, near Franz Josef. And this is a classic location, a classic outcrop, in which the Alpine Fault comes straight up out of the ground like this and is visible in the outcrop. And it juxtaposes rocks called mylonites that have come up very quickly from deep below the Southern Alps, from something like 25 kilometers or something. In a couple of million years, it juxtaposes those rocks and erodes them and forms these gravels here, which are basically brand new. So in the wall of this river valley, you're seeing a huge difference in what's going on. You're seeing rocks which have been deep, deep, deep below the Southern Alps. They've been heated, they've been deformed, they've been brought up to the surface very quickly, and now they're being eroded and laid down as gravels. There are some other rocks here. Here, quite visible is this white layer. This is crushed up rock. And this is what's formed as these rocks, as they ascend from deep below the Southern Alps, they cool and they become more brittle. I'll return to that process later, but basically as they become more brittle, they get smushed up and they form this crushed rock called cataclysite. So we went here because we wanted to drill in a place where we already knew the position of the fault and we knew something about what rocks were involved, etc., etc. So the outcrop is now sketched up in this top right-hand corner. That's a representation of the photo I just showed you. And what we did is we went up the river about 200 meters or something, and we drilled 2 boreholes, DFTP 1A and 1B. And we aimed to intersect the fault at about 100 meters in one and something like 150 meters in the other. And even though these were very shallow boreholes, I mean, these really were baby boreholes, we got some fascinating information out of them. We observed that the fault is highly asymmetric. It's asymmetric in terms of its geometry. It's not a vertical crack in the ground. We knew this already, but it's dipping. It's not producing only horizontal motion, what we call a strike-slip fault. It's oblique. And it's asymmetric in terms of other parameters that we measured. The other thing is, and just returning to one of those things I mentioned earlier, we found that as we got closer and closer to the fault zone, the core of the fault, this is where the action might happen in the next earthquake, we found that the permeability of the rocks changed by a factor of about 1 million over something like 20 or 30 meters. So we went from having these myelinites, which were remarkably permeable actually, they enabled water to flow quite easily, through material that got progressively less and less permeable until we reached the core of the fault, and then it was basically impermeable. And there was actually a pressure difference across the fault here. So, if this sort of structure persists to depth, that's an interesting thing to know about, because we recognize the importance of fluid pressures and, by extension, of permeabilities in controlling the behavior of big faults. So that was an interesting thing, even though we were only at about 100 meters or so depth. We then aimed a bit deeper. We said, right, we're going to go 10 times deeper. And the reason for doing that is because we wanted to hit the fault at about 1 kilometer's depth in order to see through the perturbations associated with the topography around the river valleys. So this is the Whataroa Valley. It's a little bit to the northeast of Gaunt Creek. And the Whataroa River is the biggest river draining the central southern Alps. It's a really big river, and when it's in flood, you know about it. We were drilling there, and like I said, we wanted to target the fault at about 1 kilometer's depth to see through the effects of these mountains on temperatures, on fluid flow, on stress, and other things. We wanted to see through them so that we could measure parameters and properties diagnostic of the deeper portions of the crust. And without going into too much detail and breaking down in tears, we didn't get there. We had a technical failure just before Christmas in 2014, and that meant that we, instead of being down as we had been at about 819 meters, we were now way back up. We'd lost the bottom portion of the borehole, and we were back up to about 400 meters or so. And it was a very sad way to celebrate Christmas, but I've got over it. And I will show you what we measured, and this was very fortuitous because before we lost the lower part of the borehole, we had installed a fiber optic cable that ran all the way from the top to the bottom to 800 meters or so. And we could use that fiber optic cable to measure this black line, which is the temperature as we went down the borehole. And we made other sorts of measurements as well. But just to give you some context, I've put on there a straight line, which is basically a line of best fit. And that tells us something called the geothermal gradient. The geothermal gradient tells us how many degrees Celsius does the temperature go up by as we go 1 kilometer or 1 meter or 1 kilometer into the Earth. And if you do that red line there, or you do it a bit more carefully and you measure the gradient, you find that it's 125 degrees per kilometer. And 125 degrees per kilometer is absolutely scorching by the standards of most deep boreholes worldwide. So this diagram on the right-hand side is a cumulative histogram of geothermal gradient measurements made in deep boreholes, deeper than 500 meters around the world. And the way to look at this is to pick on a percentage. Here, the 50th percentile, for example, go across, hit the black line, and come down. And that tells you that 50% of boreholes have a geothermal gradient of about, just about 30 degrees per kilometer. That's the global average. So if you poke a hole beneath Central Otago, for example, or the middle of Kansas, or Eastern Germany, for example, you'll get a gradient of about 30 degrees per kilometer. Now, on this diagram, we've also marked the gradients of 3 other big fault drilling projects, Wenchuan in China, Chichi in Taiwan, and Parkfield, which was the location of the San Andreas Fault Observatory project. And even at Parkfield, the geotherm is only about 40 degrees per kilometer. But the Alpine Fault's just off the chart. It's over here at 125 degrees or so, down to almost 1 kilometer's depth. So by the time we were drilling down there, we were encountering water that was above 100 degrees. So why? Well, basically, the reason it's so hot relates to what I said earlier about the action of the fault in bringing rocks up from depth very quickly. And so these diagrams on the right are a little technical. I don't want you to go through them in detail, but just imagine what's happening as rocks from deep below Aoraki, Mount Cook, are brought up to the surface faster than they know what's happening to them. They don't cool very much, and they bring all that heat right up into the shallow portions of the crust. And they make it hotter in the shallow portions of the crust than it would otherwise be. And then all this water that falls on the western side of the Alps, the orographic rain on the western side of the Alps, seeps into the rocks, seeps down as groundwater, and it extracts that heat from the hot rocks. It mines that heat out of the rocks and distributes it around the fault and the adjacent rocks. And so the gradients that we measure in DFTP2 are so high because of the combined effects of moving hot rock and then moving fluid through that rock and extracting the heat. Now, why is that important? Well, another parameter I mentioned earlier is temperature. And temperature is important here because rocks, like other materials, behave differently depending on their temperature. So as an analogy, consider two chocolate bars of the same brand. So let's take Moro bars. Take two Moro bars, put one in the fridge, put one in your pocket, and leave them there for a while. Now later, when you take them out, you take the one from the fridge and you try and snap it. Basically, you can snap it like that. It's a brittle process. That's the sort of process that's involved in earthquake rupture. Okay, it's cold, it behaves brittly, and it produces pingy fractures. You take the one out of your pocket and you try and break it, and it doesn't behave like that. It just sort of flows. It's the same material. It's the same chocolate bar, it's the same rock, but by heating it, we've changed its rheology, we've changed its mechanical properties. And so if we think about the ramifications of having very hot temperatures below the central portion of the Alpine Fault, they very likely affect the rheology of the rocks. They very likely affect where we can generate earthquakes, both small earthquakes at the present day and bigger earthquakes when something big happens. And so that's why it's important to know this. We also made some measurements we put some measurements together from this phase of drilling and the previous phase, and we came up with this composite diagram here, which sort of represented our view of what the structure of the fault was. And you can see it's not an infinitesimal zone. It's really quite a broad zone, particularly in the top few kilometers, as far as we can tell. And this zone, what we call the damage zone here, is a very active, hydrogeologically active region in which fluids are circulating through permeable rocks, probably transporting heat, probably transporting minerals. And at different points in this, let's say, 250 odd year cycle, the mechanical behavior of that damage zone is probably very different. The other thing we found, and I'll just mention this quickly, is that we made a particular measurement in the first boreholes, which, if you licked your finger, stuck it in the air and guessed, could tell you which way the fault might prefer to rupture. And this is important, as I said, because knowing where the fault slips, what direction it's propagating is important stuff. And we said, based on the drilling, we think it probably prefers to start in the southern end and rupture towards the northeast, towards Nelson, for example. So just bear that in mind. So to go deeper, we stopped drilling. We haven't gone back and done any more drilling yet, but there will be a whip around later and you can contribute. The way we've gone deeper is to use seismometers, and we record earthquakes, little earthquakes mostly, that are occurring every day beneath the central South Island and the Southern Alps. And in this diagram, each of these blobs or patches of coloured dots represents a different seismological experiment where we've gone out, we've put instruments into the ground, and we've left them there typically for a year or two, sometimes for much longer. One of the arrays has been out for more than a decade. And we record little earthquakes which we use as probes of the way the fault is behaving at the present day. And as you can see from the pictures, maybe if you've been looking at the video, it's a fantastic place to work. It's an amazing scenery. You can see like this. It's like the Lord of the Rings, but with many more helicopters. And I should say that almost all of this work has been done by graduate students. A little bit of, the odd bit of work by somebody else, but the graduate students, masters and PhD students, have basically done all the work over the last decade or 15 years or so. So I'm just pulling out one snippet of what we've learned from that. And this is a picture, it's a vertical profile along the Alpine Fault from somewhere down near Fox Glacier or Karangarua down this end up towards the Wanganui River. So it's about 200 kilometers long. And what we're showing here on this profile are the depths indicated by the grey circles and sized by magnitude, the depths of earthquakes. And what you can probably see is that the ones down in the south extend down to a depth of about 20 kilometers. Likewise, at the northern end, they also go down about 20 kilometers. But in the middle, they're confined to a zone which is really only about 8 or 10 kilometers deep. And why might be this the case? Well, we did some thermal modeling to try and figure out what might be controlling this really pronounced shallowing of the seismicity beneath what happens to be the highest topography. This is the location of Aoraki, Mount Cook. And what we found is that we can account for these earthquake depths quite well in terms of temperature if we treat the faulting here and the deformation as just exhuming rocks from depth vertically. And so you can see we put isotherms on here. The 500-degree isotherm seems to match quite nicely where the earthquake stopped. Below that, we do have an unusual phenomenon called tremor. Tremor is something we can detect on seismometers, but it seems to be a sort of very slow, burbally sort of slow motion occurring on the deeper portions of the Alpine Fault, which I'll return to later. So we do have evidence that the fault down here is moving. Even though it's not producing little pingy earthquakes, it is moving, and we see that in tremor. I don't have it on here, but there are other measurements we can make with GPS sensors. And the GPS picture is very consistent with what we've seen here in terms of where the fault is currently producing small earthquakes, but otherwise not moving, and the deeper portions where we think it's quietly slipping. Okay, so we've done all these experiments, and they've really given us a lot of information, but what we wanted to do in the most recent project is to try and record information along the whole length of the Alpine Fault, all at one go. Because most of the previous experiments you might have seen, the pictures of where the instruments were quite localized. And so to build up a picture of the whole fault, we wanted to put our instruments along its length. And that project was called the Southern Alps Long Skinny Array, or SALSA. And it was called that because it is both very long. It goes from Milford Sound all the way up to Maruia, or Springs Junction, 450 kilometers. And it's very skinny. You can see that along most of its length, it really only has about one seismometer wide. There's a few more in the middle, and then it's narrow again. And the reasons for that I won't go into here. I'm not going to talk about what led to that design. But what we did is we put out an instrument, a seismometer, every 10 kilometers on average, all the way along. And that's like putting a seismometer every 10 kilometers between Los Angeles and almost San Francisco. It's a big distance, and it was done by a very small team, some of whom survived and are here today. And we collected absolutely amazing data. It was really fascinating. This is what putting these instruments out looks like, just so you have an idea what we do. We go to a particular location, let's say here. We dig a hole in the ground until we are confident we are into the solid rock. So we're hitting, often it's schist, it will hit the schist, and once we're confident we're in solid rock, we line the bottom of the hole with sand, quartz sand. We put in a paving stone that we picked up from Mitre 10, and we tamp it all down very securely so that we have basically a nice secure foundation that's perfectly level and it's not going to rock or anything like that. We put a sensor, a seismic sensor on it, which is, depending on the model, is about that size of a loaf of bread, and the cable coming out of that goes out of the hole and is connected up to equipment at the surface which records all the data and powers the whole system. The orange thing here is a bucket, also from Mitre 10, which is just there to prevent water dripping onto some of the connections, and then we fill it all in. So the thing is really buried, and we leave it there. Ideally, we leave this part here for the whole experiment for 2 years, and with only 3 or 4 exceptions, that was the case for SALSA. The equipment performed really well. So this is just a few pictures of the team. As you can see, mostly students, mostly smiling. This is clearly at the beginning of the experiment. The work was very laborious, and sometimes we were working in quite alpine conditions, trying to find things in deep snow. At other times, we were basically operating at the peak sandfly horizon. This is where sandflies really hang out. And so digging a hole there was not as much fun as you might think. But it worked really well. The equipment remained waterproof and dry and recorded great data for a long time. And we got really cool records. And I'm just sort of illustrating how things look. If you have, in this case, 50 or 60 seismometers stretched out over several hundred kilometers. In this case, there's been an earthquake up here near Maruia somewhere, and you can see, represented by each of these horizontal wiggles, you can see the pattern of waves moving out. We have P waves, we have S waves, we have other structures in there which are telling us about the character of the fault and about the rocks it's propagating through. And I won't go through, but this is just one earthquake, and we've got tens of thousands of earthquakes of various sorts. So that was a fascinating aspect of this. We also did a whole other body of work which was looking at using these records to tell us about the actual ground shaking that would occur in the next big earthquake throughout the South Island. But I won't talk about that this evening. So I just want to extract one of the SALSA results. This is quite a new result, and it's a picture now extending for, in this case, 300 of the 450 kilometers, showing the pattern of little earthquakes which are occurring, as I said, in the top 20 or so kilometers. These lines represent where we think they start and stop. And underneath them we have a much more refined picture of where tremor is occurring. And what's interesting is that now, because we have an array which stretches for many hundreds of kilometers, we can tell where tremor is occurring and where it is not. And that's important because it means that certain portions of the fault, as far as we can tell, are just innocuously slipping at the moment, sort of just creeping along like that. But in doing so, they are probably loading up other portions of the fault. And so it's important to know where the slip is occurring and how it's loading things. So I just wanted to take a very quick diversion and tell you about something else we did serendipitously, really, while we had all these SALSA sensors out. And this was something called distributed acoustic sensing. We went to HAST, and we made use of the telecommunications cable that Chorus has been running out across the entire country. And what we were able to do there is attach a laser called an interrogator to one of the unused strands of glass within Chorus's cable. So if you take a fiber optic cable that is used to transmit your internet, and you cut it, and unfortunately they did occasionally, but if you cut it, you see many, in this case, many dozens of glass fibers. And we just took one of them, we attached a big laser to it, and we fired pulses of laser down two sections of the fiber. We started basically right here. We first of all shot along about 25 kilometers or 30 kilometers going up the coast, and then we shot for most of 6 months in total across the Alpine Fault, which is the red line, and up towards Haast Pass. And what happens is that we send a pulse of laser light, and it is scattered backwards from every point along this fiber, along this cable, and the scattering is governed by little optical imperfections in the glass. And any vibration that vibrates the cable will basically extend and contract the cable like this, and that changes the optical imperfections, stretches them a bit, and we can pick that up. So we do that 1,000 times a second, and we chop the resulting backscattered light into little sections which represent the strain or the vibrations that are occurring every 4 meters along what is about a 30-kilometer stretch of cable. So it's like having, if you do the calculation, 30 kilometers at 4 meter spacing, it's like having 7,500 odd seismic sensors that we are sampling every millisecond. So when you do that, you obtain seismic records very much like we got with SALSA, and I was sort of proud of what I showed you from SALSA, but this is the same sort of record using the distributed acoustic sensing. And I'm just showing you here a snapshot of the cable. The grey line is the highway going along up towards Haast Pass. The red line is the Alpine Fault, and the purple line follows the highway. That's the cable. And so now, we're recording these earthquakes on many thousands of separate sensors effectively. And again, you can see P waves and S waves, but there is structure in there that you can't see if you put your seismometers 10 kilometers apart. So you see a different level of detail. There are 3 local earthquakes depicted here. In each case, they look sort of the same, but with slightly different geometries, depending on where they were and other characteristics. This picture down here shows the record from a big earthquake, magnitude 7 in the Kermadex, so way north of New Zealand. And again, it has a distinct first arrival here and another one coming later. But in this case, the record is much longer. This is 200 seconds between one wave and the next. It's also got these big diagonal lines, and I just wonder if anyone in the audience would like to guess what those lines represent. Any ideas? Cars. Well, straight off the bat. Yes, cars. These are the tracks made by the good folk in Haast as they speed up and down the highway here at speeds that almost never drop below 100 kilometers per hour. And so each one of these lines is a car. And the reason for showing you this is to make the point that when you record this enormous volume of data, there are signals in it which I'm interested in, which are mostly the earthquakes, and there are signals that basically are a damn nuisance, all the traffic signals. But to the right person, which in this case is the roading authorities, that's valuable information. It tells you about the number of cars, it tells you if you're interested in how fast they were going, it can tell you something about the weights of the cars and what loading the road's being subjected to. And as we discovered in a separate experiment at Milford a little later, Milford Sound, we can also detect car crashes. And so there's all sorts of things that we can split this vast volume of data. This is a terabyte of data every day. While I've been talking about this slide, we've recorded a couple of gigabytes. So a humongous amount of data, but we can split it out for different purposes. And that's really very cool. So, you know, the roading operators of the Milford Road, they're very, very interested in bits that I would prefer weren't there. And the other thing, I won't explain this figure, but people who are experts may recognize what I'm getting at here. If we take just a small section of the fault, of the fiber, here just a 400 meter record, 400 meter section, we've still got effectively 100 geophones spaced 4 meters apart. And we can make measurements of, in this case, the waves arriving from an earthquake happening towards the southwest, which are very characteristic. And then we can try and explain those wiggles in terms of different types of fault structure, either one big wide fault like this, or just a narrow fault, or several narrow faults embedded in a bigger structure. And so we can really start to see things that are a level of detail that we can't see otherwise. So that's a really rapidly evolving area of research. Okay, so I just want to turn briefly to some work, again, led by Jamie and involving Caroline, in which we're trying to bring together the paleoseismic record of big earthquakes on the Alpine Fault with the measurements we've been making more recently and trying to come up with an idea of what might happen in the future. And in particular, we're interested in whether or not we can take the paleoseismic estimates of when earthquakes occurred, but in particular, the shaking intensities involved, how much shaking was required at a particular location to record an earthquake, and use that to constrain where earthquakes are started and which way they ruptured. So we're working here with data from several lakes, about a dozen lakes roughly, from way down here at Lake Hay up to Lake Rotoiti in the northeast. And in each one, the paleoseismic community have gone out and collected cores, which look a little bit like this in a schematic sort of format. They have patterns, patterns in the core which represent regular sedimentation, and then they are disrupted by signals that an expert can recognize as being produced by an earthquake. And then they are followed by other signals which represent the post-seismic, the post-earthquake equilibration of the landscape, basically. And so this is a fascinating area because in the past, these cores have been used. If you carbon dated material in the cores, you could work out when the earthquakes occurred. And if you compared the record from one lake to another, you could tell how far the earthquake ruptured. But now we can actually use the estimates of shaking intensity to say which way it went. So we use the lake records, which are just a fantastic resource, hard-won resource, and we combine them with measurements made along the fault that tell us which portions of the fault ruptured. And here I'm just focusing on the 1717, the most recent earthquake. So we're pretty confident that we know which portions of the fault ruptured, and we have records from many lakes of what level of shaking, here expressed in what's called modified Mercalli intensity, a measure of shaking intensity. Basically, we can quantify how much shaking was required, in this case, up towards the northern end. We can say we need to exceed a level of 7, these are Roman numerals. At another lake, we know we didn't exceed level 8, and we've got this sort of information. So one other piece of information is required to try and analyze what this means, and that is to consider different scenarios about where the earthquake nucleated. So we just consider four. We consider the case in which an earthquake in 1717 ruptured from the south unilaterally towards the north, or it started in the north and ruptured entirely south, or it started in the middle and went both ways, that's allowed, or it started at what we're calling the preferred location. And I won't go into details of why that's the preferred location, except to say that there are another fascinating strand of this research, which Russ and Tim are involved with, which is also bearing on where we think earthquakes might have nucleated in the past. So we put all that information together, and effectively what we do is run a computational simulation, and we try and simulate the waves that would be produced by an earthquake for these different scenarios, and we compare that simulated record for each of the lakes with what has been observed in the cores. And this diagram here is a very complicated one, but I'll step you through it. Basically, let's just consider this pattern here. This is if we consider the earthquake starting in the north and rupturing towards the south, and we run the simulations, then for the various lakes from Rotuiti all the way down to Lake Hay, we can produce a histogram of shaking intensities, that's shown in grey, and compare that with the red bars, which are the paleoseismic estimates of how much shaking took place in 1717. And to make it easier to see, we've highlighted the ones here in which we have a discrepancy between the grey histograms and the red ones. In other words, for this north to south rupture, at 5 of the dozen or so locations, we can't reconcile what comes out of the cores with what the earthquake simulation suggests. And likewise, if it started in the middle and ruptured both ways, we can only account for about 2/3. But if we consider the situation in which the earthquake started in the south and ruptured north, or started at our preferred location, we can account for all but one of the observations. So that's pretty fascinating. I think it's perhaps the first time that's been done, and it's all due really to the paleoseismic work that's catalyzed this sort of analysis. And it suggests that in 1717 at least, the earthquake started fairly far towards the south, perhaps right down at the southern end, or maybe at the preferred location, and it ruptured primarily towards the north. That raises the question of whether it always does that. So, and by the way, that is the same direction as we inferred from the drilling, although that particular measurement was pretty sketchy. It does raise the question of whether it always does that. I mean, it might have been that it ruptured that way in 1717, but the previous earthquake had gone the other way. So we've done this sort of analysis for the last 4 earthquakes, and the patterns we see are summarized here. So this is the most recent, 1717, these are the previous ones. And what we seem to see is that it either starts towards the southern end, a little bit like this location, and ruptures primarily to the northeast, but maybe a little bit towards the other direction, or it starts way down at the south. And so this is fascinating because it enables us to extend the paleoseismic record from dating and from the rupture extent to actually rupture direction, and that will feed into the hazard calculations. So to wrap things up, I just want to talk about what we think we can anticipate in future earthquakes. We've looked at the state of the fault, we've looked at various aspects of its state of health, we've thought a little bit about which way it might rupture, but what can we anticipate in the future? And so we're bringing together here the record from the past, the observations that are made during big earthquakes elsewhere, because when it comes to the world's biggest earthquakes, the community has to learn from all of them. Because they fortunately happen infrequently, and so every time a big earthquake happens, and I'll focus on one from Turkey, we extract as much as we can to relate to our own big fault. And we put that together with our understanding of what the current state of the fault is. So, I'm just going to motivate this by looking at one of the earthquakes that happened in Turkey in 2023, in February 2023. There were 2 earthquakes that occurred. One the magnitude 7.8, same size roughly as Kaikoura, and one following only a few hours later, which was a little bit smaller, magnitude 7.7. And these were hideous earthquakes. Collectively, the 2 of them killed about 59,000 people. So these were very damaging earthquakes. The ground shaking that was produced was much stronger than had been anticipated for these faults. And for various reasons, particularly the length of the fault, this red fault, the first one that ruptured, and the depth to which it ruptured, we think they provide useful analogues for what the Alpine Fault rupture might look like in the future. One other point to draw your attention to is that this big earthquake that kicked it all off actually nucleated on a very small fault here. This little stubby fault here, it ruptured from the star, it went due north for a while, then it hit the East Anatolian Fault and spread out in both directions. And it spread out very rapidly and caused, like I said, very substantial shaking. So here's a simulation running of that earthquake, and the simulation actually combines two components. It actually has in it an image of what's happening on the fault. This is the propagating slip on the fault, racing along the fault, and then the broader colors are showing you the pattern of seismic waves. So it's visually quite a complicated thing. And this is a very sophisticated model. It requires the world's biggest computers to run, and it embodies as much as we know about the physics of the fault rupture process and the fault and the seismic wave propagation. And yet, there are parts in this model that we just have to guess, because there are things that are very difficult to measure and have been measured very infrequently in the past. And one of them is that we've typically had very few measurements made right along the fault itself. There just aren't enough seismometers, and they're generally not put close enough to the fault to measure parameters that the modelers really need to know. So this work is absolutely important. It enables us to test ideas about how the earthquakes rupture, and yet it relies on some measurements which we really don't have well constrained. So I just want to mention two types of measurement that have been made recently, including one from this earthquake itself, that bear on this problem. And so, as I said, the magnitude 7.8 earthquake started down here. It ruptured this little fault here, which is only of the order of 20 or 30 kilometers long, and then it spread out along the East Anatolian Fault. And it just so happens that close to the fault here, only 19 kilometers from where the thing kicked off, there are two seismic stations on one side of the fault and a third on the other side of the fault. Only within, as you can see here, only within a couple of 100 meters of the fault. And the records from the two seismic stations on the eastern side are shown here. These are different components of motion. The red and the black curves are different instruments, but you can see that basically wiggle for wiggle, they're recording the same thing, which is, it's just verification that we're not recording spurious signals. And the characteristics of these wiggles tell us that even only a few kilometers after it had started rupture, this earthquake was traveling at speeds in excess of the seismic wave speeds. So this is what we call super shear, because the propagation front, the pulse of rupture, was propagating faster than the shear wave speed of the rocks, which governs the propagation of the seismic waves and the shaking. So this is an extremely rapid propagation. It's like what happens when a plane breaks the speed barrier, the sound barrier. It generates a similar sort of sonic boom, but this is happening in the ground. So if you had been standing up here, for example, you would have felt the fault rupture before you felt the seismic waves hit you. And this sort of phenomenon is very important in some of the rupture simulations that I mentioned earlier. These measurements bear on how the rupture initiated, how it evolved in the first few kilometers of rupture, and then this transition to the super shear, extremely fast rupture, provides a lot of insight into why the ground shaking was so strong. And you end up with something called a double punch, where you end up with this sonic boom type shaking happening, and then a slower shaking arrives a bit later. So there are many reasons why this data set is absolutely important. Now, this is a funny diagram to put in, but this is just a chronology of the last 25 years showing records of big earthquakes, bigger than about magnitude 7, and they're colored here according to whether or not they produced super shear rupture. And these are only big strike slip earthquakes. That is mostly sort of basically vertical planes rupturing only in a horizontal sense like this, unlike the Alpine Fault, which is rupturing like that. But nevertheless, you can see that for the bigger earthquakes, bigger than roughly 7.5 or so, most of them, at least more than half, seem to propagate at super shear speeds. And so it is interesting to ask ourselves, is the Alpine Fault capable of doing the same thing too? The other really novel measurement that's only been made in the last few months is highlighted here. And before I explain this slide, can I just get a show of hands? Who has seen the video? Yeah, okay. Oh, we might as well go home. But just to remind you, Anybody who hasn't seen the video, this is a CCTV video recorded at this red location here, several hundred kilometers south of where a big earthquake started, only about 100 kilometers south of where a big earthquake started in Myanmar in March. And the earthquake started at the Yellow Star, ruptured all the way down this very straight fault. And it just so happens that here there was a CCTV security camera that recorded not just the shaking, you can see the gate shaking, and this is just a snippet, but also the far side of the fault, like that, just moving by several meters. So we could sit here all night watching this video, and that would be fun, but this guy here, Jesse Kurse, who's a graduate from this university, and many people here have worked with him, Jesse didn't just do that, he took the video and he digitized every frame. And he compared the motion of the far side to this side, and he had various reference points that he could use to make sure he calibrated things correctly. And using that, he was able to extract this red curve here, which is a record of how the ground shook when the fault actually slid. Or sorry, not how the ground shook, but how the ground moved when the fault actually slipped. And you can see that it only took about 2 seconds. And in that time, it slipped at about 3 meters per second at peak velocity. So, you know, if you think about this fault, and if it was like the Alpine Fault and only produced a big earthquake every 250 years, it was, at this location, it's only doing something for a couple of seconds, then it sits there for the next 250 years. This is absolutely vital information for the modeling efforts, because it tells us about how concentrated the slip pulse is. How fast it's traveling is one thing, but how much slip occurs and at what speed at any particular location on the fault is absolutely vital information. And so it was serendipitous, it was put on YouTube, Jesse got hold of it, he took the time to do the work, and he's extracted records which are absolutely vital. It's the first time the fault motion like this has been recorded with a camera. So, just to wrap up, okay, what should we be doing? I mean, I've sort of been saying that the Alpine Fault's got this great record of big earthquakes. It ruptures remarkably consistently on sort of 250, 300 year basis. We're late in that cycle. And we've seen elsewhere how making measurements close to big faults can give really important measurements, either about super shear or about the length of time it takes for slip to actually occur at a point on the fault. And so the question I'd like to finish with is, what should we be doing to record signals that we expect to occur in the next few years or decades, so that we get the most information out of the next Alpine Fault earthquake? And I should emphasize again, this is information if we recorded it during an earthquake, which would not be of particular benefit to the people of Hokitika or Whataroa or Christchurch. This is information to feed into the global efforts to understand earthquake physics. So what should we do? And I first started thinking about this several years ago when this paper came out with the title A Grand Challenge, International Infrastructure for Earthquake Science. You know, how do we take the next step in understanding how the Earth is working in big earthquakes? So, there's a time-limited offer, and again there'll be a whip around for this project as well. But here's the Alpine Fault seen from offshore looking obliquely. And what we could do is we could go to a spot, an accessible spot like this, and we could put various sorts of instruments out across the fault. So here I've just extracted a portion of the fault, and I'm showing here clusters of instruments of various sorts, spaced 10 meters from the fault on either side, 100 meters from the fault, 1,000 meters. And there are different sorts of measurements, what we call strong motion, designed to record the strongest shaking that takes place when an earthquake rupture occurs, GPS or GNSS recorders to record the larger static offsets, broadband sensors to record the very small processes happening before and perhaps afterwards, pressure and temperature, and some distributed acoustic sensing optical fibers for good measure. And because, I mean, I've tried to tell you that we are working on this, but we don't exactly know where it's going to start, which way it's going to rupture. We have ideas, but we can't be confident. So we'll have to make these measurements at a number of locations along the fault. And if we did that, and the fault ruptured, we would collect, and everything was working, we would collect data which are absolutely vital to understanding how big faults rupture. And I would say that this is one of the preeminent places to do this because it's a fault whose chronology of earthquakes we understand better than anywhere else. There is nevertheless a bit of a problem, and that is we'd be in this for the long haul, potentially. So we do have a good idea about how often the Alpine Fault earthquakes occur and where we are in the cycle, but it might not happen for years, might not happen for decades. It might have already started, actually. It might have started just a few minutes ago, and shaking hasn't arrived here yet. But we could be in this for years or decades. And it would be a very intimidating funding proposal to put in all that infrastructure, all those different types of sensors, and keep them operating reliably so that at the time something exciting happened, they were all recording what they should have. We'd need to spread our bets. We'd need to put this infrastructure along the fault. And we'd have to be making measurements which were good from day one. We couldn't just sort of pin it all on recording the next big earthquake. You'd need to be making important observations about the Alpine Fault from the day you started this. But given that this is a Wellington audience, you'll be able to relate to this. Just like with ferries, there is the Rolls-Royce option, and there's the Toyota Corolla option. And the Toyota Corolla option here, and I know there's at least one Toyota Corolla driver in this room. That's a really cheap option. The Toyota Corolla option would be to just put little pairs of strong motion sensors along the fault, maybe every 10 kilometers, and cameras, wherever you could put a camera in. You'd put a camera in to try and record what's going on when it actually breaks. And you could do this for a much more modest cost. And it is a less infrastructure, fewer measurements, but nevertheless, just as we saw in Turkey, you could record vital information to feed into this understanding of big earthquakes. So that is the lower cost option. And so I just put it to you, just imagine what you could record if you went down this weekend to Franz Josef, which is here, and you filled up at the petrol station and just thought about how you could get this project up and running. This is the main road heading down towards the glacier, and as anybody who's driven that knows, as you go down the road, you go over a slight bump. That's the Alpine Fault, and run through the back of the petrol station, through the hotel, the motel over there. And there's actually a camera there already, but it's pointing the wrong way. It's pointing up the road. It probably is visible if you know where to look. But you could stick a camera there on the weekend, a GoPro or something like that, and be getting set to record things. And I'm being a little bit facetious here, but I think it is something we should be doing. If we think this is important and we think we understand how the fault behaves, we should be preparing to record things. And I've just taken the opportunity here to just overlay on this diagram Harold Wellman's map, just to show you again where we're talking about. These are some sites where there are roads crossing the fault. You could get to either side of the fault. You could do things like that. And I put it to you that this is something we should get on with. So to summarize then, the Alpine Fault's record, the paleoseismic record of past earthquakes is almost unparalleled worldwide. And it gives us a really impressive body of quantitative body of information to think about the future. The fault produces earthquakes regularly, very regularly compared to other similarly large faults, and it's late in this typical cycle between one earthquake and the next. We've made all sorts of measurements along the length of the fault and then vertically into the ground that tell us about the state of the fault, where we think it's hot, where we think it's producing little earthquakes and might deform brittly, at least at the present time. And they should be incorporated in our models going forward. We shouldn't just treat the fault as just one uniform rectangular block. We should incorporate that information. We're making measurements using new techniques, such as this distributed acoustic sensing, which give us sort of unparalleled insight into processes happening on meters, tens of meters, or hundreds of meter scale. And we're making steps to try and figure out which way we think this fault has ruptured in the past and potentially will rupture in the future. So that analysis is really important. We're combining contemporary measurements with the long-term record to say something about the future. And finally, I do think that the global earthquake science community, not simply the New Zealand community, but the global community should recognize this fault as somewhere to be making preparations to record observations next time the fault ruptures that would be of vital interest in understanding large earthquakes. And that's it. Thank you very much. Ngā mihi.